Welcome to the Divergence and Integral Tests, section 5.3. So in the last section, we attempted to determine the convergence or divergence of series by calculating the sequence of partial sums. And as you probably quickly found out, that is a very tedious way to determine if a series converges or diverges. So the rest of this chapter is going to be devoted to various other types of tests that will help us to determine if a series converges or diverges. And so we're going to start with the divergence test. As always, if you want a complete in-depth analysis of the divergence test and where it comes from, there are plenty of other videos out there, and the textbook as well does an analysis on this. My goal here with these videos, as always, is to apply the divergence test to actually determining convergence or divergence. So first of all, the divergence test says if the limit as n approaches infinity of a sequence, now let's be very clear here, this says we are taking the limit of a sequence, a sub n. If the limit of the sequence does not equal 0, if it equals c, or in other words, it has some limit which is not equal to 0, or the limit does not exist, then the series diverges. So the short way to remember this, if the limit does not equal 0, the series diverges. If it does not equal 0, if the limit does not equal 0, it diverges. So what happens if the limit does equal 0? Well, if the limit does equal 0, then we have no idea. Inconclusive. And then we need to go on to another test. So the divergence test is a good first test to determine if a series diverges or converges. If the limit of the sequence does not equal 0, it diverges. If it does equal 0, then we need to proceed to another test. So let's just do a few divergence test problems here. So our first one, the series from n equals 1 to infinity of n over 3n minus 1. We want to know if this series converges or diverges. So we're going to take the limit of the sequence. And so we've done that. We did that in section 5.1. Taking the limit of the sequence, there's various techniques. In this one, you could simply apply L'Hopital's rule. The derivative of n is 1. The derivative of 3n minus 1 is 3. And so the limit ends up being the limit of 1/3, which is 1/3. 1/3 does not equal 0. All right, so the limit of the sequence is 1/3. That's my c value, which is not equal to 0. Therefore, the series diverges. And we're done with it. We know that it diverges. So we would not need to apply any other tests once we conclusively determine that this series diverges. Next. So the series from n equals 1 to infinity of 1 over n cubed, if we take the limit of the sequence, we can clearly see that that equals 0. And so therefore, the test is inconclusive, and we don't know. We would have to go on and do another test. I believe I wrote this one wrong, or at least it wasn't very clear, so I crossed this off. In case there was any doubt, this is supposed to be e to the 1 over n squared power. I'm not sure if it really looked like that or not. So if we take the limit of the sequence, e to the 1 over n squared power, as n approaches infinity, 1 over n squared approaches 0. And as 1 over n squared approaches 0, e to the 1 over n squared approaches 1, because anything to the 0 power is 1. So therefore the limit is equal to 1, which is not equal to 0, and therefore we conclude that the series diverges. So the divergence test is very simple to apply. It gives us a quick and easy way to determine if the series diverges, and if it does not diverge, then it's inconclusive. We don't know for sure. Which means, as I said, we need to come up with a new test. And that's where the integral test comes into play. First of many different tests that we're going to have to determine the convergence or divergence of a series. So first of all, it says, suppose a series with positive terms, there exists a function and a positive integer n such that the following three conditions are satisfied. Number one, the function has to be continuous. Well, pretty much in calculus, all the functions that we deal with are continuous. The function is decreasing, and in a previous set of notes, I showed you how to determine if something is increasing or decreasing. We basically did that when we were looking at the comparison tests. And then finally, the function f of n is equal to the sequence a sub n for all n greater than or equal to n. And n being greater than or equal to n is positive, which means all of the small case n have to be positive. So basically what this comes down to is three things have to be true. The function has to be continuous, decreasing, and positive. And in most of cases of these problems, we technically should go through and show that they are continuous, positive, and decreasing, but they almost always are. So I'm just going to assume that that is the case. However, if you'd like to verify that, you can just do that. So this is the conclusion of that. Basically what it says is the series and the function value, the series and the function value both converge or both diverge. So what this is saying is that to determine if a series converges or diverges, we're going to create an equivalent integral, a function, and we're going to integrate, I should say, an equivalent function. So the function is equal to the sequence. We're just replacing the n's with x's. And then we are going to integrate the function. And if that integral converges, then the series converges. If the integral diverges, the series diverges. That's the basic gist of the integral test. So let's put it into action here. First problem. Here's my series, 1 over n cubed. Let's apply the divergence test, first of all, just to develop a systematic way of approaching these problems. So with this particular test, we have 1 over n cubed. So if I take the limit of 1 over n cubed, then we see that the limit is equal to 0, and therefore the test is inconclusive, and we need to go to another test. And so that test is the integral test. So I create a function 1 over x cubed, which is equivalent to the sequence 1 over n cubed. And 1 over x cubed, you can graph it in Desmos. You can picture what it might look like in your head. I'd say just graph it in Desmos if you want, and determine that between 1 and infinity, the function is continuous, it is positive, and it is decreasing. That's the simplest way to go about doing that, rather than doing it algebraically. So we set up the integral from 1 to infinity of 1 over x cubed dx, and now we just want to integrate that. But of course, the upper bound of integration is infinity, so this is an improper integral. And so we have to integrate this the way that we learned when we were doing improper integrals. So we're going to take the limit as b approaches positive infinity from b to 1 of x to the negative 3 dx. I just brought the x cubed up to the numerator, made it x to the negative 3. Okay, so integrating that, we get the limit of, as b approaches positive infinity, of negative 1 over 2x squared, evaluated from b to infinity. That becomes the limit as b approaches infinity. We now substitute, we now substitute the b in for x here, and we substitute the 1 in for x there. And now we can see that as b approaches infinity, the denominator here is going to get infinitely large, so the entire fraction is approaching 0. And of course, the limit of 1/2 is equal to 1/2. So we have the limit is 0 plus 1/2 is 1/2. So the limit is 1/2. So the limit So the integral is approaching 1/2. And so because the integral converges to 1/2, the series will also converge. They both either converge or they both diverge. Next up, we have the series from 1 to infinity of 1 over the square root of 2n minus 1. Once again, applying the divergence test, if we take the limit of the sequence, 1 over the square root of 2n minus 1, we can see that that approaches 0, and so therefore the test is inconclusive and we need to do another test. So let's use the integral test. We set up an integral, and we simply replace the sequence with an equivalent function. And again, as always with these problems, our upper bound of integration is infinity, so we have to do an improper integral. So the limit as b approaches positive infinity from b to 1 of 1 over the square root of 2x minus 1. We're going to have to use some U-substitution here. And so basically, letting u be equal to 2x minus 1, du is equal to 2 dx, or dx is equal to du divided by 2. And so that's where all of this comes in. This is my du divided by 2. And then, of course, I'm taking the square root of 2x minus 1, bringing it upstairs and making it u to the negative 1/2 power. So integrating that, I didn't show that work either, but you can show that when you integrate u to the negative 1/2, you're going to end up with the square root of u. And then replacing 2x minus 1 in for u, we have the square root of 2x minus 1. And we are evaluating that from b to 1. And so replacing b in for x and replacing 1 in for x. Now, the square root function, so as b is approaching infinity, the square root function is an increasing function. So it's increasing over its entire domain to infinity. So therefore, as b is getting infinitely large, this is continuing to increase and increase and increase towards infinity. So if either one of these terms is approaching infinity, the whole thing is approaching infinity. And so it's infinity. And therefore, the integral diverges. And since the integral diverges, the series also diverges. In the last one here, let's use purple. My series, 2n over 3n squared plus 4, applying the divergence test. If we apply the divergence test and we take the limit of the sequence, we can see that it does equal 0, which again you can get by just applying L'Hopital's rule a couple of times. And so therefore we need to apply another test, the integral test. And so we set up an equivalent integral, and it is an improper integral. And so we have the integral, we have the limit as b approaches infinity of the integral from b to 1 of 2x over 3x squared plus 4. And this is another U-substitution problem. I showed that this time over here. So letting u be equal to 3x squared plus 4, du is 6x dx, or dx is du over 6x. And so I substituted all that stuff in here. The x's will cancel out. The 2 and the 6 becomes a 1/3. And then we end up with du over u, which is going to be a log problem. So we have the limit as b approaches infinity from b equals b to 1 of 1/3 du. Now we actually integrate that. And we get 1/3 the log of u, which then replacing 3x squared plus 4 in for u, we have 1/3 the log of the absolute value of 3x squared plus 4, evaluated from b to 1. Substituting b in and substituting the 1 in, Logarithm function is also an increasing function over its entire domain to infinity. And so therefore, as b gets infinitely large, this whole quantity here, the logarithm, is getting infinitely large. And so since this is approaching infinity, it doesn't matter what's going on here. If either one of these terms is approaching infinity, the whole thing is approaching infinity. And so therefore, the integral diverges. And because the integral diverges, the series also diverges. One more. In this series, I changed n from 1 to 0. I think that was supposed to be a 0. Not that it's going to make a lot of difference. It'll make it a little bit easier to evaluate the integral at the end. So again, if we were to apply the divergence test, we would see that this is approaching 0, as taking the limit as n approaches infinity. Well, we have an n in the numerator, so it's getting infinitely large. And then e to the negative n squared. Sometimes people like to rewrite this as n over e to the positive n squared. So either way you look at it, n squared here, this is getting infinitely large. So this whole thing is getting infinitely large. So this is the denominator is getting, this is getting infinitely large. Okay, they're both, the numerator and denominator are both getting infinitely large, but an exponential function gets larger faster than a linear function. And so the denominator is getting larger faster than the numerator, and therefore the whole thing equals 0. And by the divergence test, it is inconclusive. Okay, so that was the divergence test. The divergence test shows that the limit of the sequence is 0, and therefore the test is inconclusive. We need to do another test. All right, so we create an integral. Once again, it is an improper integral. And so we take the limit as b approaches infinity from b to 0 of x e to the negative x squared dx. This is another U-substitution problem. Letting u be equal to negative x squared, du is negative 2x dx, dx is du over negative 2x. Substituting that in, which is what I did here, the x's will cancel out. We get this negative 2 in the denominator, which comes out in front as a negative 1/2, e to the u du. So we've got this to integrate. And so integrating e to the u is easy. It's just e to the u. So we get the limit as b approaches positive infinity of negative 1/2 e to the u. Substituting negative x squared back in for e to the u. And then evaluating that at b and at 0. And so this term becomes 0. The easiest way to see that is to rewrite it like I did over here. Because you have a negative exponent, let me go back up here, use this space. So if we take e to the negative b squared and make it 1 over e to the b squared, it's easier to see that as the denominator gets infinitely large, the whole thing approaches 0. And I think we've discussed similar situations in other videos. And so then e to the 0 is 1. So this is 0 minus 1 is going to be minus 1. Minus 1 times the negative 1/2 becomes 1/2. And therefore, we may conclude that because the integral converges to 1/2, now again, it doesn't matter what the integral converges to. It just matters that it converges to some value c or L. So as long as the integral converges, then the series will also converge. And that is the integral tests. So we now have two tests, the divergence test and the integral test. And I'm going to real quick show you one more test called P-series. This isn't really so much a test. This is just a type of series, right? So a P-series is any type of a series where the sequence is 1 over n to the p, okay? You have n raised to some power. Think of p as being a power, all right? So 1 over, or it doesn't have to be 1 over, it can be any constant in the numerator, a constant in the numerator divided by n raised to some power. So you can think of it as a power series, P series. No, don't think of it as a power series, that's something else. But a P series, that means it's raised to a power. Now, if P is greater than 1, then the series is going to converge. If P is less than or equal to 1, the series diverges. So if you can identify a series as being a P series, it's extremely easy to determine if it converges or diverges. So, just a few real quick examples. Here's a problem. First of all, let's apply the divergence test. Okay? Applying the divergence test, we see that the limit of 1 over n to the 4th is 0, therefore it is inconclusive. Then we say, hey, this is a P-series. And because the p-value is 4, p is equal to 4, that's the power, and that's greater than 1, the series converges. That's all there is to it. The series converges. In the next one, again, by the divergence test, it is 0, inconclusive. We notice that it is a P-series, where p is equal to 2/3, which is less than 1, and therefore the series diverges. And 1 over n to the 5/3, p is 5/3, which is greater than 1, therefore the series converges. And this one takes a little bit of playing around with sometimes. They're not always going to be this straightforward. Sometimes you're going to have to do some algebraic manipulations, like we're doing here. Well, you take n times the square root of n, rewrite that as n times n to the 1/2, multiplying them together, you get n to the 3/2. Well, p is 3/2, which is greater than 1, so therefore the series converges. Now, in reality, very few series that we deal with are actually going to be P-series, but we're going to use P-series in other tests. One of the next tests we'll be doing is called the comparison test. And so we will be comparing a series to a P-series, and we can tell very easily if the P-series converges or diverges, but I don't wish to get ahead of myself. All right, that is it for this video. There's only one more video for this section, and it's going to be a very short one on estimating the value of a series.